Okay, we want to get into a frequency domain analysis. And in order to do that, we need to understand sine waves. So remember, frequency domain analysis is anywhere where we have frequency on the x-axis. And I'm just going to put some magnitude over here of something. So we have some time domain, and that's a separate presentation type of analysis. And down here, we're going to have a frequency domain. Oh my goodness, it's early. Analysis. In a frequency domain analysis, what is on the x-axis are specific frequencies listed here. And maybe this is 1, 2, 3, 4, so forth. What's also represented here, so this means a signal, and in this case, it's going to be a sine wave, and we're going to get into this, with a frequency of 4 hertz. And then we plot a data point for that right here. And this would be some magnitude. I'm just going to put here with a magnitude A. All right. So the frequency domain plot that you always want to watch out for frequencies on the x-axis is simply telling us a sine wave and a frequency and an amplitude of that sine wave. What will frequently you'll see in a frequency domain analysis are plots with multiple frequencies plotted with multiple amplitudes. All this plot is telling us is that this frequency plot has all these sine wave pieces of information, and for each sine wave, there's a corresponding magnitude. So if I look at this sine wave here, it would have this magnitude here. Let's just use this as a 10 hertz, and maybe this is a magnitude of 2, it doesn't matter. So this is a sine wave of 10 hertz, 10 cycles per second, with a magnitude of 2. Now, what some references will do, and I've certainly have done this, instead of plotting individual data points like that, you may actually see, and I'll just do it over here, magnitude, frequency, you may see bars. It may be a bar chart where each bar represents one of the dots. Or sometimes you'll see the dots connected and you just see a line like that. This is still that, but in here is the detail of the different frequencies included in this type of plot. We just did lazy and use a line as opposed to individual dots. Or we do a more of a bar chart like this. Any of these ways are fine. Sometimes we do this, sometimes we do this, sometimes we do this. It all depends on the point that we're trying to illustrate with the frequency analysis. All right, so I've gotten into this, what the end goal is, but what's really important is to understand the components of a sine wave. All right, so let's, just almost unplugged my camera. Let's look at the sine wave in a little bit more detail here. got another pen here. This one's about to dry out. All right, so your sine wave, this one's no better. Your sine wave has the general equation, like if you put in your calculator, you'd probably put in sine of theta and you get some number out. And that's helpful, but that's a single data point. What we're going to use is the more general form of the equation, a sine 2 pi f t plus phi or phi, depending on how you want to do it. Or you can use a sine omega t plus phi or phi, where in this case, well, let's go through each one of these. So either of these equations are fine. They say the same thing, but you'll see the omega is 2 pi f here. So omega equals 2 pi f. All right, let's go through each of these. So A is the amplitude of a sine wave. All right, let me draw a sine wave here. Very symmetrical sine wave. This is time down here, and this is amplitude over here. What we're looking at here is the maximum amplitude here and the minimum amplitude here, and that full range is A. Okay, that full range is A, the amplitude of a sine wave. 2 pi is, you should recognize that as a circle, 2 pi r, a circumference of a circle. F is the frequency of how fast this sine wave is repeating. I'll go through that in a second here. T is the moment in time that we're interested in. And this symbol out here, phi or phi, either way, is what's called a phase shift. What that means is this sine wave may start over here, or may start over here, or over here. So it's just a phase shift. So a lot of times I don't mess around too much with the phase shift in this equation, because most of the things I do, I deal with sine waves starting at time 0. And omega t is just a shortened version of writing out 2 pi f. Okay, so one key component we've already identified here, we actually identified 2 of them, but one key component we've already identified here is amplitude. The other one is how long it takes this sine wave to repeat, and that's t, or the period, all right? That's how long time to complete one cycle, or one repetition of a sine wave. All right, so we can now we can combine t to get frequency, or we can use t to get frequency, and frequency in hertz is always cycles per second. Okay, that's what a hertz is. 1 cycle per 1 second is 1 hertz. All right. So given that that we're dealing with this repetitious motion, really what this is a circle that you plot out over time, as opposed to drawing a circle in XY coordinates. All right, so what we actually would write here is frequency is 2 pi radius of or circumference of a circle over t. So that's our relationship between 1 cycle per time to complete that cycle. All right, so this is all, this is all information you need to understand frequency domain analysis. because the frequency domain analysis is predicated on understanding sine waves. And a sine wave, we need to look at two real key components: the amplitude of the sine wave and the frequency, or how often it repeats the cycle. Those are two pieces. This is the phase shift. And again, I don't mess too much with that, especially early on. And so then we can create our sine wave in Excel by creating a time column worth of data. Create one second worth of data, spaced apart by 1/1000th of a second. And then enter the constant for sine wave frequency, multiply that by 2 pi, take the sine of that and multiply that by the amplitude of the sine wave. So you can create your own sine wave in Excel and plot it out simply by creating that time column first, and then making a constant and make frequency a constant, and then set up your Excel equation to include the 2 pi ft, take the sine of that and multiply by your amplitude. And it's a neat way to explore different sine waves in Excel or in MATLAB if you're doing this in MATLAB. All right, so now let's look at frequency domain analysis in a little bit more detail. There is a Fourier transformation theory. So, and it's actually fast Fourier. Oh, that's not good. I'll try again. Fast Fourier transformation. Oh, there's an R in there. All right. All right. What this we just refer to as FFT. What this theorem states is that the time domain analysis and the frequency domain analysis are interchangeable. I'll just put Y over here. I'll put frequency here. I'll just emphasize the hertz. I'll put time here. I'm going to put A here. What this transformation states is that these two analyses are interchangeable. If I have time domain data, I can get frequency domain data. If I have frequency domain data, I can get time domain data. They are the same. They're the same information. They're equivalent to each other. All right. There's nothing unique. Sorry. There's nothing special about either one of these. But there are times where we can see things better in the time domain, and there's times that we can see things better using a frequency domain. An analogy I often give is because a lot of people have experience with looking at 12-lead EKGs or have seen 12-lead EKGs. And the whole idea of a 12-lead EKG is simply that you're getting information about the electrical activity of the heart from different perspectives. And one perspective may be better than the other at times, but they're all telling you how much electrical activity the heart has. Well, that's the same thing here. These are just different perspectives. And there's times that this is a better analysis to do or look at the data from this lens versus this lens. And there's times that this one is better to see things in the data than this one here. All right. And the more that we do this, you'll see there's going to be times where you're going to say, nah, I really want to do a frequency domain analysis. And there's other times where you're going to say, no, time domain is what I need. I've done a lot of work in shock attenuation during running. And early on, we thought it was really valuable to do a frequency domain analysis of the acceleration data that we were recording at the leg and the head segments. Well, what we also had is a technique to look at shock attenuation in the time domain. And what we ultimately were able to tease out is that even though the frequency domain gave us a little bit more granular understanding of shock attenuation, the analyses in looking at the time domain or the frequency domain ended up being exactly the same. So what we were able to do is to show that you could do either analysis to understand shock attenuation. So you did not always need to go down a frequency domain analysis in order to understand shock attenuation during running. So yeah, so I actually started moving away from using frequency domain because it was a little bit more abstract. Not everyone fully understands the frequency domain. The time domain analysis is easy. You can see it. It's what we're used to. And we're used to seeing time on the x-axis. This just throws a little bit of a curveball, a little different perspective. All right, so what the Fourier transformation theorem states, I don't have the exact wording, but we can take any time domain signal in here, all right, whatever it is, all right, that's not going back in time, whatever the time domain signal is, we can represent with a bunch of sine waves. And just like in the last set of notes, maybe these sine waves added all together are the best representation of the time domain analysis. So again, I get lazy and sometimes I'll write it out like that. This is saying that if I take all the sine waves illustrated here and I add up all those sine waves, I'll get exactly that signal. This, if we take this signal and we look at all the sine waves that make up the signal, I get exactly this information. So these two pieces of information are equivalent, even though they may look different, because our brain is telling us that this is time down here, but it's not time. This is telling us specific information about sine waves. So let me start another page on that. All right, so the FFT, the fast Fourier transformation, is simply the algorithm to take your time domain data and transform it to the frequency domain. All right, so let's just look at this a little bit more. What that concept that I just drew in the previous notes, I'm going to put time down here and I'm going to put a sine wave here, like that. This has some period, some frequency, okay, and it has some amplitude. So this is sine wave 1. Well, let's say I have another sine wave below that. Now I'm going to do these in the same time column or same time axis here. And maybe I have a sine wave like that. So this is sine wave number 2. And you can see this amplitude, I'm going to make this a 2, I'm going to make this a 1, just so we can see it, okay? And then maybe I have another sine wave, and I'm going to make this really small amplitude, but a high frequency, meaning it's going to repeat a lot more cycles in the same time period. So maybe we make this, 0.25, just for sake of. All right, what we're doing to go from, well, if we're really in the frequency domain, which is almost what I'm doing here, to the time domain, what I'm actually doing is I am adding up I'm going to add up every one of these magnitudes at the same moment in time. All right, I add them all up, and maybe I get something that looks like, I'm not going to do a very good job here. All right. Yeah, okay. You get the idea. This should be a little bit more regular than that, but add point by point. And by doing that, I get a new signal. Well, this would be our time domain signal. This is what we would record from our instrument, is this signal right here. Okay, to complete my example here. This is what the fast Fourier transformation basically states, that this signal is mathematically made up of these three sine waves. Okay, now I created that signal by first creating these sine waves. Okay, we're ultimately going to measure something in time, and then we're going to work backwards and figure out which sine waves best add up to create the time domain signal. And we have two things we can manipulate with sine waves: the amplitude and the frequency. Okay, how quickly this repeats. So this frequency of 1, maybe I make this a 1 hertz. Maybe the frequency of 2, we'll make that a 2 hertz. And maybe frequency of 3, maybe just for sake of example and how I drew it, maybe that's a 10 hertz. Repeating 10 times per second. Repeating 2 times per second. Repeating once per second. All right, maybe, well, in this case, I created a signal by creating 3 sine waves. I got this. The fast Fourier transformation takes this information and then decomposes that time domain signal into the frequency components. And the way that we would plot out this frequency information, I'll do it over here. I don't want to put it under that same plot. I'm going to put amplitude. I'm going to put frequency here. And I'm going to put 1, 2, and I'll put 10 all the way over here. 1 has an amplitude of 1. This is not actually correct, but that's okay. I would get that type of plot. And again, I could use bars here, or I could connect the dots, but I would get 3. This is my frequency domain because I've got frequency on the x-axis, and I've got 3 dots representing the 3 sine waves that best represent this signal. Now, if I do this in Excel, if I do it in MATLAB, I do this exercise where I create a time domain signal from 3 sine waves, and I get that signal. And then if I take that signal and run it through the fast Fourier transformation algorithm, I will get exactly that information from that transformation. And this transformation, FFT, this transformation tells me that this time domain signal consists of 3 sine waves. One with a 1 hertz with this amplitude, a second sine wave of 2 hertz with this amplitude, which is greater than that one, and a third frequency of 10 hertz with the least amplitude, which is exactly what I drew. And I can do this in Excel and prove the point too, that the math all works out. Well, as you can see now, I can go in either direction with this information. I can either look at the time domain and generate the frequency domain, or if I have frequency domain, I can actually generate time domain. That's called an inverse fast Fourier transformation. So going in the other direction from frequency and creating your time domain information. So let's see, where am I? I'm page 4 here. All right, so this concept is critical to using EMG, to creating filters where you have a cutoff frequency, or you have some, either a high pass or a low pass or a band pass type filter. Because what you're doing in a filter is you're basically taking some frequencies and saying, I don't want those frequencies in my time domain signal. I'm going to set that amplitude to 0, in essence. So I set that to 0, and I will smooth out. I will set that amplitude to 0, and then I only end up with 2 sine waves that will make up my time domain signal. And that jaggedness that I've tried to draw in here goes away. So that's called a filter. And I can get rid of specific frequencies, or I can get rid of ranges of frequencies. Like maybe I don't want this low frequency information in the signal. I can pass the data through the filter. I'm going to set these two to 0, and now I'm only going to end up with that signal, if that's the signal I'm interested in. Or I can set a band of frequencies to pass through the filter. There's all different ways I can do this, but I can do it specifically looking at the frequency content of the time domain signal. So this becomes a powerful tool to start trying to understand the time domain signal. Okay, I think I'll stop there. I know I didn't talk about EMG on this too much, other than doing a frequency analysis of EMG is very common because there's lots of frequency content in the EMG signal, and there's a lot of smoothing that often goes on in a processing of an EMG signal, and you really need to understand the concept behind smoothing in the Fourier transformation. Okay, I hope that's helpful.